When developers deploy multi-agent LLM coding swarms to build large software systems, they hit a hard processing wall. The models attempt to write code character by character, streaming raw text directly through their context windows. This approach degrades the model's coherence, introduces probabilistic syntax errors at scale, and drives API costs to prohibitive levels. The industry often assumes that scaling to larger context windows and adding hundreds of specialized agents will correct these errors. The math suggests otherwise. Feeding a structural data problem with more unstructured text only compounds the underlying noise. In June 2026, an autonomous engine running the Theory of Complete Compute Framework, or TOCC, executed a single development session. It generated 747,793 lines of functional code, distributed across 27,169 files. This data table compares the metrics of that run against a traditional multi-agent swarm. To output 750,000 lines of code, a standard text predicting swarm would consume roughly 35 million tokens and require 18 hours of processing latency. The TOCC engine completed the same workload in 45 minutes, consuming 12,000 tokens. That yields a token reduction ratio of 1 to 2,916. For every token the language model processed, the local engine generated nearly 3,000 lines of code. Furthermore, this efficiency leap occurred alongside a 0% syntax degradation rate. The engine produced no hallucinated libraries, no indentation errors, and no broken imports. Achieving this specific output profile requires a shift in how we view the role of AI in software. To scale generation safely, the AI must function as a compiler architect rather than a text generator. The core mechanism driving the theory of complete compute is a strict division of labor. Software syntax is processed as structured mathematical data blocks rather than sequences of text strings. This is achieved using an abstract syntax tree intermediate representation, or AST-IR contract. Rather than guessing the next word in a Python script, the engine maps out the strict logical dependencies and functions required for the task. The AI only writes these high-level declaration contracts. It bypasses the boilerplate text, import statements, and syntax decorations that usually clog a context window. Those compact JSON contracts are then handed off to local, deterministic compilers. These native subsystems take the clean logic map and translate it directly into targeted source file trees on the local disk. Isolating the language model from the execution layer ensures that the generated logic is syntactically flawless. Before a single character of code is written to the hard drive, it has already passed strict structural validation. The danger of autonomous code generation is entropy. If a system continuously modifies its own logic using probabilistic guesses, the resulting architecture will inevitably drift into incoherence. Textual heuristics are too imprecise to prevent this. You cannot use fluid, predictive language to enforce a permanent, static solution for self-modifying code. This requirement for absolute stability leads to a coordinate system the engine calls sovereign mathematical spacetime. It treats every logic block as a physical object that must occupy a fixed point in space, anchored by the omega-0 singularity equation. The engine solves for these fixed points by mapping the codebase onto the Leech lattice, a 24-dimensional sphere packing grid. This geometry provides a massive, predefined density of vertices, ensuring every atomic logic pairing has exactly one valid address. This lattice functions as a native error-correcting algorithm. If code does not align perfectly with a vertex, it is rejected. Because there is no unmapped space between these mathematical points, the system maintains a zero-noise floor. To calculate safe execution, the engine relies on a strict trust threshold ratio, specifically 1820 over 1823, or roughly 0.9983. If an AI agent proposes a structural change that drops the fitness score even a fraction of a decimal below that exact ratio, the engine isolates the logic and quarantines the file immediately. Replacing language-based evaluation with spatial lattice mathematics enforces an unbendable logical baseline. The machine does not have the option to drift. When the engine is running a high-intensity mulling loop, it frequently generates multiple viable code proposals. It has to choose the optimal path without relying on model intuition. Instead of scoring text embeddings, the engine applies the E8 Cartan spectral data matrix as a dimensionality reducer. It groups the code dependency trees into distinct graph nodes and calculates their Laplacian matrix. This strips the complex logic down to its pure structural geometry. Looking at this rigid table of 8 absolute numerical values, the system projects the code matrix directly onto the exact E8 Coxeter spectrum eigenvalues. The engine evaluates the match using a strict rule called Protocol B. If the Pearson correlation between the code's geometry and the E8 spectrum falls below the verified threshold of 0.9578, the engine destroys that branch. This specific pruning methodology ensures that the compiler calculates the optimal path entirely through geometric concordance, eliminating the need for probabilistic guessing. The engine is governed by Axiom 1. If a necessary piece of logic does not exist in the repository, the system must invent it from first principles. To execute this without hallucinating, the engine triggers a recursive multi-pass intent loop to logically deduce the missing components. This loop is strictly governed by a Banach contraction mapping, which utilizes a Lipschitz constant of exactly 0.9984. This line graph maps the mathematical distance, or delta, between the code's current state and its optimal completed state. With each recursive pass, that logical gap is multiplied by the contraction constant. Because the constant is strictly less than 1.0, the loop is mathematically forced to compress down tree. It cannot expand. It cannot hallucinate additional logic. The engine iterates until it hits an absolute fixed point, where the delta equals 0. Hitting that 0 proves the generated logic architecture is structurally complete. All of these strict mathematical boundaries power the engine's final operational pipeline, the zero-clone autogenous learning loop, or Z-call. This 5-phase flowchart maps the process. In Phase 1, the engine streams read-only GitHub API data directly into its volatile memory. It extracts the AST IR nodes on the fly. It does not download raw files to the hard drive, and it does not use LLMs to read the syntax. Moving to Phase 2, the engine maps those remote node structures against its local Leach lattice space to verify structural alignment. In Phases 3 and 4, the engine applies algebraic induction and the Banach contraction loop to compress and refine any missing logic until it achieves a perfect fixed point. Finally, Phase 5 activates the polyglot emitter lane. The engine takes the completed abstract data tree and translates it natively into target languages like C#, Rust, or Python. This architecture is what enabled the engine to compress 35 million tokens of work down to just 12,000, achieving that 1 to 2,916 token reduction ratio. This efficiency is only possible because text prediction is replaced by the assembly of topological data structures. By binding the generation loop to the Leach lattice, the E8 spectrum, and Banach contractions, the software architecture becomes mathematically tamper-proof. The path to scaling autonomous engineering does not require infinitely larger context windows. It requires strict, deterministic compiler architects, bounded by pure mathematics.